Okay, good morning, and we're going to go ahead and start our recording of today's lecture. And so the first thing is to kind of go over some announcements. So I need you guys to submit your homework. Look, it's due. It's time to move on. I know this online stuff's a little bit challenging, but we got work to do. And look, if you're running into some difficulties, you just need to send me a message in Canvas, and I'll help you out. The other thing is I need you to finish up your measurement day digital work, right? You need to submit that so that I can do the next step, which is to collate your stuff and put it together so that I can share it with the class. All right. So the other thing is that I sent out some messages for you. I want to check in with you and see how you're doing. So please reply to my survey request. So this is a rebroadcast of the Chapter 3 Exploring Data description section. So I had run into some problems with my video, so I'm re-recording it, and so this is where we're headed, so through Chapter 3. Okay, so we start off by talking about what's kind of a boring little subject, right? And seems sort of obvious, but collections of observations, well, that's what data are. And of course, data can be of all kinds of flavors. And so at some level, it seems bewildering, like everything is kind of out there and different and whatnot. Then there's some structure. We can think of measurements falling into two different categories in terms of the kinds of data that are acquired. So we speak of data types. Those of you who are programmers, coders, you'll know data types are a really important part of understanding how to put together applications, right? And so in statistics, we have data types as well. And there's some overlap between what computer folks do and what statisticians do. So let's kind of define them right up the bat, and we'll show you some examples and justify why I will be asking you about data types throughout the semester. All right, so the two basic categories of data types, observations are going to fall into categorical types, and so those include binomial, ordinal, and nominal. So binomial, that means that the observations fall into one of two classes. Either they are positive or they're negative. They're present or they're absent. It's yes or a no. If you have more than two categories, then the binomial becomes nominal. So if it's yes, no, and maybe, that's a nominal type of category, right? And then the one in between is something that you're going to be familiar with, which is the idea of ranking. So, obviously when you're thinking about individuals who run the 100-meter dash, they finish with a specific time down to the second, right? Down to the millisecond, actually. But if you think about it, what really all that matters at the end of the race is who came in first, who came in second, who came in third. So performance measures like that, we often then only record who came in first, second, or third, and so that's an example of an ordinal data type. Okay, then the other category, the other broad type of data, are the continuous variables or quantitative variables. And so we begin, of course, by the simplest one, which is we just simply count. There's no, half measures. You're either looking at a litter of puppies or whatnot. There's no such thing as 4.5 puppies, is there? So those are countable. If you look at scales on fish, you can count them. And so those are often called meristic traits. All right, so then the next level of a continuous variable type are those that are called interval. And so these can be half measures. These can be 1.2. They can be 3.7659. And the difference between 1 and 2 is quantifiable, right? It it's a measure in itself. It's a difference that can be quantified down to the decimal. Whereas in like ordinal, the difference between 1 and 2 is not static. So first versus second doesn't mean that somebody finished just 10 seconds behind. First versus second can be, the difference can be minutes, hours even. Okay, so that's the difference between ordinal and interval. The difference has measurable units that are consistent throughout the scale. One thing about the interval scale that distinguishes it from the ratio scale, which is also the same as in like 1.2 minus 1.2 units, that's meaningful, hence the idea of the ratio, right? But the difference between interval and ratio scale is that there's a true zero for ratio, or at least conceptually there's a true zero. So going back to interval, the classic examples of interval measurements are degrees Celsius or degrees Fahrenheit, where the zero is set arbitrarily. The only temperature scale that would be ratio scale is Kelvin, because the true zero has a physical reality. Whereas degrees Fahrenheit, what's zero? It's 32 degrees below the freezing point of water, right? So that's completely an arbitrary setting. So no true zero for interval, true zero for ratio. Okay, so let's kind of run through some examples. So when you're throwing darts, for example, you might measure the distance between the center and your toss. What kind of a data type is that? Well, you could certainly say, did I hit the target? Yes, no, right? So that observation would be categorical, binomial, but for distance between the target and the target center and where the dart landed is clearly ratio scale. So take a moment and kind of try to fill these things out yourself. So for example, leaf color, green, green, yellow, yellow, is that categorical or continuous? Weight, is that categorical or continuous? Okay. How'd you do? Well, it really helps to know what the units are, right? So the color morphs, green, green, yellow, yellow, is clearly nominal. You're either green or you're not. So if we were just comparing green versus not green, that would be binomial. But we can look at the different leaf colors and we can identify green, green, yellow, and yellow for a particular mutant strain, in which case then the data type is nominal, categorical. So the rest of the examples, so for example, infrared temperature gun, all right, the units can be either degrees Celsius or degrees Fahrenheit, so clearly then that means it's an interval. Lung volume, expiratory, respiratory volume, so you blow out as hard as you can, and if you can measure that, the units would be a volume, right? And so that's clearly ratio scale. Okay. So the point being, it's a fundamental part of your statistical reasoning to be able to define the observations that you've made. And that's not just talking about how you got them or what they mean, but it certainly means whether or not they have qualities of being categorical or continuous. So clearly continuous, if you look at the units, that's going to tell you if it meters, miles, etc. Those conceptually can have, you can travel 0 miles. You can have a volume of 0. Rates, instantaneous rate, no movement whatsoever, so the time is 0. Indexes, okay, so where you combine different numbers or measures, okay, they often end up not having units if they're the same kinds of measures, so a numerator versus denominator kind of thing, but indexes are often, in fact, almost always going to be ratio scale. Okay, and categorical, well, names of persons, names of places, names of species. Those are classic examples of nominal data type. presence, absence, yes, no, well then that's clearly binomial. Okay, so where you can kind of get confused is that often, we're talking about categorical data types, but numbers are going to be reported. You're simply describing how many individuals have a certain property, and then you count up the yeses and you count up the nos. So while certainly 5 and 9, it sounds like that's countable, so it must be continuous. It's like, no, it applies to the variable itself. What's the data type for the variable? Not the results, but the data type applies to the variable. So this is an example. I went to randomlists.com and said, why don't you grab 1,000 male names and then count up the most frequent one that showed up randomly. And so this round, Bryson came up 5 times out of 1,000, and that was the most numerous. So I would report it as 5 yes and 995 no. But the point is what's the data type? Categorical binomial, because it's yes, no. Okay. So the next thing we need to talk about is we're measuring variables, okay, and variables are measured on selections of individuals or sampling units, experimental units, drawn from the population from which they come. And so parameters apply to characteristics of populations. So we use variables to estimate parameters, okay? Now, clearly, variables vary from individual to individual. Good to know, right? But parameters do not vary. They belong to the population from which individuals are selected. Okay. So one of the things that we're going to have a little bit of issue with, you guys being biologists for the most part, right? So you're going to be thinking about population as collection of individuals. But more technically, the population we're referring to is a collection of observations of a particular trait or feature. It's okay to think about them as individuals first, but that you just have to be aware that in the statistics we're talking about a little bit more narrow definition of what a population is. Okay, so we're not going to spend a great deal of time worrying about this, but I wanted you to get the definitions out right away about what we're measuring are variables that are features of populations, and so variables are estimating parameters. Parameters pertain to the population, variables pertain to the samples of individuals, and of course, since we can sample different individuals, we would expect the variable itself to change, right? Okay. Now, this is going to look a little intimidating, but as I've tried to introduce you to the idea that you're going to get bogged down in using R and R Commander and doing the homework problems and whatnot, but doing statistics is conceptually not that really challenging. Looks like my formatting got a little crazy here, but so we'll explain this as we go through. But you're always working with samples from populations. The only exception to that, of course, is if you're doing a census, and so there are situations in which a census applies. 2020, every 10 years in the United States, the idea is that we count every single person in the country at that particular time. So that's a census. It takes months and months and months to do. But there can be other examples of where you do a census. So for example, if you're working with endangered species, it's not too far of a reach to think that you may know of every single individual of that endangered species, in which case if you do work with them, you're doing census work, right? You know every single individual. But more often than not, what we're doing is we're pulling samples from a population, and we do our work on the samples, okay? And so the technical aspect is we're looking at, say, height or some other trait, and so we can ask, can it conceivably come from a theoretical probability distribution? And then we'll end up with what's called a sample distribution, okay? So the idea is that if it can, so in other words, individuals will vary more or less in a normal distribution sort of way, well, then you're clearly working with data types that are continuous. And what you're going to do in terms of statistics, right, is you're estimating parameters about the population. And there's a whole host of tests, t-tests, ANOVA, Bartlett test, linear regression, general linear model, right? A whole bunch of tests that are about working with samples to estimate parameters about the population. On the other hand, if your data doesn't come from a probability distribution, you're dealing with categorical traits. These are called non-parametric. So there's a whole bunch of statistical tests that are associated and used if you have non-parametric data sets. All right, so here we go. This sounds like a lot of work, but if you actually recognize it, the first thing that you do is you recognize what kind of data you have. If it's continuous or categorical, then that directs you to the kinds of trait or statistics that you can use. So the other point about this slide is this red arrow. Notice that it's just unidirectional. So if you measure data and the type is continuous, whether it's interval or ratio scale, okay, or even if it's countable, right? You can always rank them from smallest to largest. And so in other words, the point being, you can always convert from continuous to categorical. And prior to the wide application of computers and software specialized for dealing with large amounts of data, it wasn't unusual for people to take continuous data and crash it down into categorical data in order to, make their point. And so you should appreciate that while you can do that, you probably shouldn't, because if you think about it, remember, who came in first, who came in second, doesn't tell you about whether the race was close or not. Continuous, you can tell, okay, the person who ran second finished just tenths of a second behind the first place, and that's really a close and exciting race, whereas a person might have come in second and been dozens of minutes behind, and so that wouldn't have been a close race, right? So you lose information from the categorical when you convert from continuous to categorical. We'll spend just a tiny bit of time about the idea of measurement. There's a whole, body of work about measurement and instrument validation and whatnot. Validation means the idea is that the instrument actually measures what you think it does. And so there are classic examples where some fairly sophisticated instruments don't necessarily measure what you think they do. And this is a much, much larger issue in, say, psychology. So, for example, back in the early 1900s, Binet came up with the IQ test, right? And offered it as a way of measuring intelligence, right? And you should appreciate immediately that coming up with the number as a score from an exam doesn't necessarily tell you about intelligence, right? It's not a particularly good instrument for measuring what we think intelligence is. So that the IQ test is not a valid assessment of intelligence. It doesn't mean it doesn't have some use, but you got to be really careful with that. Another, issue about instrument validation. So hopefully you know something about the Elizabeth Holmes and the Theranos story. So she, over the past, 10, 15 years, had been trying to sell a device that she said could measure hundreds of blood tests based on a drop or two of blood. And of course, that actually is physically impossible, but she did a fantastic job of selling the idea. And if you could do something like that, that would be really cool. But experts in the field kind of warned her early on that her idea was kind of silly. But at any rate, she was able to sell this idea. And so they built a device, and they proceeded to, of course, draw blood from people and whatnot. And what they were finding, of course, was that the instrument was highly inaccurate. So it didn't agree with industry standards. It also lacked precision. So repeat observations on the same sample. Remember, they were working with little blood drops, so there wouldn't have been a lot of sample to work with. But at any rate, they could go and get repeated blood draws from individual. And so the instrument, depending on the chemistry that they were looking at, would give wildly different results on the same samples. And so the whole story about it, she, in her company, the higher-ups sort of deceived a number of people, from investors to certainly patients and customers, about the accuracy and precision of the instrument. And there was also, of course, questions about whether it was actually measuring what you thought it was supposed to be measuring. Okay. The other thing about measurement is the idea of missing values. And so this is a really important subject. So the first kind of rule is that when you're entering data, you only enter the value 0 if it's truly 0. Otherwise, it's going to be a missing observation. So you can think of missing values as being of at least 3 different kinds. And so one of them is structurally missing. In other words, if you're going to ask certain questions, there may not be a way that the person can actually respond to it because, of course, the category doesn't apply. A classic example is to say something about parents. You know, tell me who your father is. Tell me who your mother is. And clearly there's whole groups of people who are adopted or subject to other diverse family situations, and so they can't answer that. And so that's a poorly worded question in a survey. And so missing values, they skip it. They can't answer it because you didn't account for the possible answers. And so it'll be a missing value, but it's not because of like an error or something like that. So there's a reason why it's missing, right? Another way to think about it is that irrespective of the treatment, you can have missing values, right? So there's no systematic pattern in why a missing value. If somebody just forgot to record it, somebody chose not to answer it, but there's no correlation between treatments and the missing values. So as long as those aren't huge in terms of the number of observations, if you have lots of missing values, that obviously weakens your study. But as long as there's no association between the missing value and the treatment type, then this isn't going to have an effect on your outcome, right? Reduces your statistical power, increases your confidence interval a little bit, and we'll talk about that. So you're going to be less sure of your results. But since there's no association between missing and a treatment, it's random with respect, and so that weight that equals out in the analysis. Okay, so the last one though is a big one, and there's a whole bunch of reasons for there to be a missing value, but it's not at random. So an example of that is, so I was working with a data set here some years ago, and so they're using an instrument to measure chemistry. And if you know something about measuring chemistry, you know that the machines have limits. So if you have too saturated of a sample, the readings flatten out. They peg at a top reading, so like a spectrophotometer, the absorbance reading doesn't go above 3. But the other is the idea that if you have a very dilute sample, right, the chemistry is still there, but it's below the detection limits of the instrument. So the idea that missing not at random, there's a real reason why the instrument's reading 0 or the instrument's reading 3. And so you wouldn't want to analyze that data thinking that 0 is 0. So it's a missing value. You don't really know what the true value was. It's the limitations of the instrument. So this is all about the idea of measurement. Accuracy, how close to the true value is your observation. Precision, when you repeat observations over and over again, how close are they to each other? Validation, the idea that the instrument is actually measuring what you think it does. And then finally, missing values and the qualities of why an entry is missing in your data set. Okay, waiting for the slide to change. Come on. Okay, sorry about that. All right, so here we go. Some other issues about reporting numbers is, of course, the idea of significant figures. So in your introduction math courses, they probably spent some time playing around with significant figures. Your lab courses in your first year may have spent some time on this. Certainly physics, they do this because having a precise reading may require lots of zeros after the decimal, right? So at any rate, some general rules about significant figures. Don't get in the habit of rounding observations. Always record the raw numbers. So if the instrument measures or reports a value of like 0.03, don't report it as 0.1, right? Write it out as much as you got. The other point, of course, is never round during calculations. At the end of doing your calculations, when you're about to report, that's when you apply the theme of significant figures. So, excuse me, so that's going to depend on the instrument's precision, how many figures after the decimal that you add. So it's safest to assume that the last digit isn't precise, but so it could be off. Okay, and so when you buy a new instrument, there'll be some discussion about its precision. Okay, so in general, you're going to round to this. So if it measures to 0.0001, you would round to 0.001. But that's, again, after all the calculations have been done. Okay, so let's get to the heart of the chapter 3, which is about exploring data. It's kind of a first thing that you do. So we'll talk about the other aspect of exploring data in chapter 4, which is basically making graphs. Okay, but let's talk about statistical ways to describe the data. So basically two properties. You describe the middle, and then you describe the variability about the middle. So this next several slides are about the middle. And it applies to continuous data types, right? You can collect a whole bunch of height measurements on people, and you can simply ask for that sample, given as X bar, okay? What are the most common, what's the middle look like? Okay, so you've already done, in many, many cases, calculated the mean, the arithmetic mean. And so, for example, if the observations or the measures are 4, 5, 6, 7, and 8, I can have 4 samples that were 4, 1 sample was 5, 3 for 6, 2 observations for 7, and so on, okay? So I would add up all of my samples, okay? And that would be my sample size of n. And then I take up all of these 4s, 5s, 6, 7s, 8s. So 4 individuals with 4, 1 individual with 5, 3 individuals with 6, 2 individuals with 7, 5 individuals with 8, and I'd add those up over and over and over again to get the sum, and then divided by the sample size. That's the sample mean. Given the way I've represented the observations, it would be easier to do what's called a weighted mean, which is basically the weight is the frequency. So that'd be 4 out of, what is it? 4 out of 15, right? So 4 divided by 15 times 4. Add that up with 1 divided by 15 times 5. 3 divided by 15 times 6, and so on. And then sum up the weights, which of course should equal 1. And we'll get our weighted value. And it should be the same thing, right? Okay. So in R, if you want to practice this, this is a pretty simple little code, right? So introducing our R, you know in coding that you often want to make notes to yourself. So if you don't want, when you enter code into R, it will work on whatever you get it, right? So if you want to tell R to ignore what you're writing, you just put the hash sign in front of it. And so this will not be used by R in any way. But so here's our command. So this is our first, sharing of how to get data in. There's lots of different ways to do that. But so remember I said there were 4 observations of 4, 1 observation of 5. So I just simply entered all of those values. And C means combine, and so we're going to create an object called X. And we think about them as variables, but R is a more general programming language, so these are technically objects. But this is how we assign our data to X. Okay, where's my cursor? There it is. Okay, so once I've done that, so I would enter this at the row, and then, or at the line, hit return, and then I now have that in memory. And so if I want to get the mean, I just simply write mean, parentheses, X, hit enter, and that's the value. Okay, so I did the same. Let's do the weighted mean. So this is how you would get the weighted mean. Okay, so I put the data in as Y, just because I wanted to keep it different from X, right? So X is still in memory. I could have overwritten it, but I didn't want to do that. So that's bad programming. Always create a new object. Okay, so I entered, what's nice about using the weighted mean is I just entered my observations, 4 through 8, and then I put in the weights specifically. 4 15s for 4, 1 15 for 5, and so on, right? And so I could enter a check to make sure that I hadn't made a typo in my command. So I just add them all up, the weights, and of course it should equal 1. And then the command for weighted mean is, get ready for it, just weighted dot mean, and then I give the observations, comma, the weights, and of course, there you go. Okay, so there are other means. It depends on the kind of data that you're working with. So for example, the geometric mean, you can't have, to calculate the geometric mean, you can't have values that are negative. Harmonic mean is another one. So harmonic mean works with ratios or frequencies or rates. So a lot of time when people do miles per hour and calculate miles per hour, they do it as the arithmetic mean, and what you should be doing is the harmonic mean. Okay. Geometric mean is often used when you're doing, say, gene expression studies, and that's because the expression measures that you're going to get for each gene, you compare them one after the other, they can be quite different, so they're on different scales, and so you use the geometric mean for that. But both of them, while they're unusual sounding and whatnot, are just descriptions of the middle. It's just the application is appropriate given the kind of data that you're working with. Statistical reasoning. Okay, so to get the geometric mean in OR, there isn't, unless you load a specific package, it turns out that there isn't a command for geometric mean or harmonic mean, so I have to give you a formula. Okay, and so remember, the course is about statistics, not about programming and learning R necessarily. And so this is an example where, you know, I would say definitely use Microsoft Excel or Google Sheets or the open source and free Office package called LibreOffice has a wonderful spreadsheet program called Calc, and I use that as my default spreadsheet program. But at any rate, they have functions, geomean and harm mean. So of course within the parentheses would be your data. So you might, if I ask you to do the geometric mean, you just go, okay, I'll just do it in Excel. And it's like, cool, because again, all I'm asking for is the answer, not the process. Okay, so we had four different kinds of means that we defined. So let's talk about other measures of the middle, and you're probably familiar with these as well, the idea of the median. So you take half the observations, you order them from smallest to largest, and then half the observations below and half the observations above. That middle one's called the median. For even numbers, you repeat, but you might take, that means that you're going to have two that are the same, so you take the average of the two, basically divide them by 2. And in R, you just go median, your object, and return, and 6. Okay. Mode is a very common way of thinking about it, particularly if you have, you know, categorical traits. You're going to ask about, you know, how many individuals are this and how many individuals are that. And so you might simply say, well, the description of the middle is the one that's the most frequent observation. So that's the mode. So this is a whole bunch of ways of saying that R doesn't calculate the mode easily. So in the book you'll notice that I have written a little function for you. Again, it's easier just to go ahead and maybe use Excel or another spreadsheet program to calculate the mode. Okay, so let's relate these measures of the middle. So if the data are normally distributed, okay, the mean and the median will be the same. But if the data are skewed, so this is a right-tailed skew, there's an observation that's way off to the right, okay, what'll happen is that the mean is sensitive to this outlier, and so the mean will be greater than the median. So the flip, so what about if all of the observations are out here and there's only a couple of individuals that are measuring, no, that's called a left-tailed skew, okay? So what would happen to the mean and the median for the left skew? Well, the mean will be less than the median for a left-tailed distribution. So that's why if you have a non-normal distribution, you report the median. It's a better representation of the middle than the mean because the mean is sensitive to outliers. Okay, so the next level of describing your data, we just got through talking about the middle. But of course, that's not going to describe the whole data set, is it? Where the next level of question is, how variable are the data in your data set? Do individuals pile up around the middle, or are they scattered about the middle? So I did a simulation here, so the mean is 10 and 10, so the middle is the same, but clearly these are very different data sets, right? So I simulated a larger standard deviation, which is a measure of variability, 50 versus 5, and so of course the spread of points is much greater and much less here. So you need, the basic idea then is when you're describing data, at minimum you need to talk about the middle and the variability about the middle. Statistics of variability. All right, so if you're doing a census, then of course you can calculate a measure called the population variance, take the square root of that, and that gives you the population standard deviation. And the point about doing a census is that that's it. You just count and you can describe but you don't do statistical tests on them because you're not drawing samples from a population. You simply report the numbers. Okay? The formula for the variance, I want you to think about, again, these different equations. It's like vocabulary. So there are certain elements of statistics that you should kind of start recognizing. And one of them is this idea, where's my cursor again? There we go. Individual observation subtracted from the measure of the middle. That difference is used repeatedly over and over and over again in all the different equations and tests of statistics. Excuse me. Okay? And one of the tricks is to square that difference, which means, of course, that becomes positive. And you add up that difference over and over and over again for each individual observation divided by the population size, and that's called the variance, sigma squared. Okay? One of the ways you can use the standard deviation is to normalize your data set. You correct individual observations against the mean divided by the standard deviation, and that gives you what's called the z-score. And this is something we will spend some time with in chapter 6. So I'm just kind of giving you an idea of how knowing something about the variability, it allows you then to figure out how common that observation will be in your data set. Okay? This is called a statistical table. It defines the height along this curve, and z is along this axis. Right, so z 0.0, that's there, and it doesn't. This should be a frequency of 50%. Okay, but we're working with samples, and so collection of observations on a sample of individuals, we can calculate the sample variance and the sample standard deviation, simply the square root of the sample variance. The formula looks very much like what we had before. Instead of the population mean, we now have the sample mean. But the basic part of the equation, individual observations, subtract off the mean, square that difference, go on to the next, and the next, and the next, all the way up to the sample size. Statisticians found out a long time ago, though, that if you don't do something, the sample standard deviation gives you a biased estimate. Bias means that it doesn't give you the true value as often as it should. And so there's a systematic problem with this measure, and a simple little correction. Bessel was the first person who came up with this idea. It's just simply, if you take the sample size, subtract off 1, the performance of the statistic is better if you don't do that. So that's a technical way of introducing the idea that statistics don't always, the equations don't always estimate what you want, and so statisticians over the years have fixed those equations, and that's why you use the n-1 to fix it. Okay? In order to calculate the standard deviation, just simply SD, parentheses, the object, hit return, and boom, there you go. Okay? Another measure of variability is called the standard error of the mean. And this is appropriate when you're doing an experiment. If you're not doing an experiment, if you're just collecting and describing observations, then the standard deviation is the appropriate way of reporting variability. The standard error of the mean is defined as the standard deviation for the sample divided by the square root of the sample size. So of course, the standard error of the mean is always going to be smaller than the standard deviation, and it is a way of thinking about your precision about the true population mean. Other measures of variability. Range. My guess is that you've done the range too. So if you recall, when we're calculating the median, the algorithm is arrange your values from smallest to largest. So if you take the largest one and subtract the smallest one from it, that difference is called the range. When you use the command range, then your object R reports the minimum value and the maximum value, but the actual range is simply the difference. Another measure of variability is the absolute mean deviate. Take your individual observations, subtract off the sample mean, but then take the absolute value of that, repeat that over and over again, then divide it by n. So clearly this is a way of giving you a positive number, and the larger the number, of course, the greater the variability. Alright, so there are situations where while you're describing your data sets, you may want to make comparisons of the variability for the different variables that you're measuring. Alright, so what this slide's introducing you to is another statistic that's about variability, but it's used when you're going to compare different variables. And in particular, it's important that you don't try to compare standard deviations by themselves, because it turns out the standard deviation is a biased estimate in the sense that it's correlated with the sample mean. So the larger the sample mean, the greater the standard deviation will be. So coefficient of variation is a way of crudely correcting for this positive relationship between the mean and the standard deviation. So you just simply divide the standard deviation by the sample mean, multiply it by 100, and that gives you a reasonable way of comparing how variable your data are. Okay, so 26.7% for our x value. That's the level of variation. All right, so let's apply this. So are mice and elephants similar for body mass variability? Obviously, you know what a mouse is, and a mouse is a pretty tiny animal. It's about 25 grams, whereas an elephant is, of course, much, much larger. And so the mean size is clearly much greater for elephants than it is for mice. So I came up with this little data set. Apologize for the Disney cartoon image from the Jungle Rhythm. If you know anything about, well, we'll leave that for you, but it's a picture of a mouse and an elephant, right? Okay, so I found some data for the size of individual elephants and the size of a group of mice, same number, and put it in kilograms, which is the natural, if you will, units for measuring elephant size, and then converted the grams of mouse to kilograms. So my goodness, really big difference. And so we want to compare the variability. So here's my descriptive statistics, the mean, and here's the standard deviation. So obviously much, much bigger, right? That's thousands of times greater. But because there's the correlation between the standard deviation and the mean, you can't compare the standard deviations. They're biased estimates of variability. They're correlated with the mean, so you use the coefficient of variation. And so, not surprisingly, the elephants are more variable, but that number now is much more reasonable to make comparisons. It's been corrected for that correlation with the mean. Okay, so that's going to be the end of my Chapter 3 discussion. So have a nice day.